efficient orbital relaxation in the excited electronic state, which is inherent in the linear response TD-DFT. However, state average REKS, because it's a variational method, provides a better description of the orbital relaxation and therefore better description of the excited state.
Have you checked the character? I think that also double excitation is also important here.
Here, these are homo-lumo vertical transitions.
Homo-lumo. Yeah. Okay, lowest.
Mm-hmm.
I see.
Yes, that's our lowest homo-lumo transitions. So they're quite simple from say formal point of view, but not so simple for linear response TD-DFT. Right. Okay, we have already seen that even the simplest methodology with 2 electrons in 2 active orbitals provides good description of many interesting situations important for describing dissociation, chemical reactions, of course, involving dissociation of chemical bonds, 1 electron excitations, and crossing between the ground and excited electronic states. Well, if we want to go beyond this simple active space, we need to extend to larger active spaces, such as 4 electrons in 4 orbitals. So this implementation is still quite rudimentary. It's not available in Games US. It's available only in TerraChem at a very, say, rudimentary level. But already this simplest, let's say, extension of the REKS methodology provides very interesting results for many, say, important situations. For example, well, I will briefly describe what this methodology is.
I think that this is a good point to stop because
I will quickly go through these slides.
Wrap this up. Yeah.
I will quickly go through these slides. So for the ground electronic state, I have already shown this energy expression, which is derived from application of GVB formalism within the context of density functional theory. The ground state energy, for example, does not, I mean, that energy which I shown in the previous slide does not correctly describe dissociation of double bond between carbon atoms, for example, in ethylene molecules, because the dissociation curve will go to a wrong dissociation limit, although it flattens out, but there is some energy difference between the correct dissociation limit and this curve. And this is due to the necessity to recouple the spins on the dissociated fragments. So we have singlet molecule, but in the end, we end up with 2 triplets coupled to a singlet. And this is really a difficult situation, which is not simple for GVB. It can only be described by extending GVB formalism, or because REKS method is based on the application of GVB, extending REKS formalism by adding more and more configurations. So this lists all the configurations which I included there. So open shell singlet configurations of various types, where I describe 1 electron transitions within GVB pairs and between GVB pairs. So this is within specific designated GVB pairs. And these transitions are between designated GVB pairs. And also some other open shell configurations, such as double open shell singlet state, doubly spin polarized state, and simply double excitations from the lowest perfectly spin paired state. So these configurations can be included into state averaging or into state interaction schemes. So more explanations, I will skip this for. Right. Of course, I've shown previously 9 configurations, 9 configuration state functions. It would be not very reasonable to include them all into the state averaging, because some of these configurations are very high in energy and it will deteriorate the description of that.
Well, as I already told you, I think these are fork building. So we share the integrals.
Yes, yes.
I don't think that there's any much.
Right. Therefore, I tried only a few ways to include states into state averaging. for example, by taking perfectly spin paired state and two open shell configurations, open shell singlet configurations, where transitions occur within GVB pairs. For example, if B and C are pi, pi star, and A and D are sigma, sigma star orbitals, it's natural to include sigma, sigma star into one GVB pair, pi, pi star into the other GVB pair. And I supplement these ground state perfectly spin pair configuration with two open shell singlet configurations, where I consider only single excitations within these two GVB pairs. This is one way, 3 state, state average, REKS 4, or I can try to supplement the perfectly spin paired state with doubly spin polarized state. Doubly spin polarized state, I will explain a little later. This is a superposition of two triplets into one singlet. All right, so two triplets combined into one singlet. So this is, I show it only symbolically here, but you can believe me, this is indeed that.
Okay, hey. Michael, I think it's too much details for the people.
Yeah, right.
Yeah.
I solve, say, for these equations, I obtain the orbitals for this or that method, and then I include all 9 states, which I shown before, into the secular equation, solve the secular equation, and obtain 9 excitation energies. So I'll skip this slide. And from this computation for the dissociation of ethylene molecule, I obtain now correct dissociation curves, so that the lowest state, the ground state, goes exactly to the limit of 2 carbene in triplet states. And as a, in addition to this ground state, dissociation of the ground state, I obtain also several other dissociation limits. Green curve corresponds to dissociation into 2 singlet carbenes, and this can be checked by calculating energies of the of 2 independent singlet carbenes and comparing with this energy. Or you know that singlet carbene can exist in 2 singlet states, low-lying singlet states. One is 1A1 symmetry and 1B2 symmetry, and the other curve, this dotted curve, corresponds to dissociation into 2 carbenes in 1B2 state. So all that is very nice that now this methodology can properly describe dissociation of a double bond. But besides that, so I'll skip this slide. It is very well designed to describe excitations in dimers. So this is a very simple example of dimer. I think that this is quite important example, ethylene dimer. And in dimers, we will have in the perfectly spin paired state this configuration, because we have 2 identical units here. So we have a ground state pi, pi star orbital on one ethylene, pi, pi star orbital on the other ethylene, and the respective local excitonic state. So excitation on one monomer unit and excitation on the other monomer unit. Now the other states will describe charge transfer excitations or double open shell singlet. So we excite both monomer units into singlet lowest, into their respective lowest singlet state. So this is another configuration, or triplet configuration. So we have triplet state here, triplet state there, but overall they are coupled into singlet state. So this will be that. And of course, 2 doubly excited states. And for this, we can obtain very interesting, say, pictures for the lowest excited state as function of distance between the 2 molecules and CC bond length. I kept all these symmetric, of course, same bond length, CC bond length, and the same geometry. Otherwise, for the 2 ethylene units, and using 2 different optimization schemes, I obtained very similar picture, where S1 and S2, these 2 surfaces, represent local excitonic states, either excitation on one or the other. Of course, they will, due to interaction between the 2 monomer units at finite distances, they will split the 2 states. There will be in-phase combination of the 2 local excitonic states, S1, and out-of-phase combination of the 2 local excitonic states S2, but there will be multi-excitonic state S3. And multi-excitonic state at certain geometries crosses the two local excitonic states. And this crossing between the states is, in my opinion, important for the description of phenomena such as, I will skip this for one, such as singlet exciton fission, for example, where the standard model of a singlet exciton fission is the following. So we excite a dimer system, so molecule 1, molecule 2, typically these are polyacenes, into local excitonic state, such that one monomer is excited, the other remains in the ground state. Then this local excitonic state crosses with the multi-excitonic state built of two triplets, triplet on one monomer, triplet on the other monomer, coupled overall into a singlet state. And then this multi-excitonic state dissociates into two independent triplets by changing the geometry, of course, of the monomer units. And this methodology, which I have outlined briefly before, is capable of describing these, say, crossing between local excitonic and multi-excitonic states and mixing of local excitonic and multi-excitonic states. And I think that it will be also applicable to, I never applied it and never thought about this application of this methodology, to energy transfer. So imagine that we have excited one monomer unit and want to describe the rate or the event of excitation transfer from one monomer unit to another monomer unit. Right, so in that case, of course, mixing with multi-excitonic state will become important. Mixing between local excitonic states and probably some mixing with charge transfer excitons will be also important. And all these states, for example, charge transfer excitons, are included
so
into
this part is really promising because these days people is talking about the new solar cell material based on the singlet fission, and also people talking about triplet fusion into a singlet, and all these things. They don't know much about it. I think that this is a good way. Well, by the way, do you have a gradients for this so that we can?
For that method, I did not implement them, but I think that it's feasible to say.
Okay.
First, one needs to derive expressions for the gradient and then implement them. All that is feasible. Only question of the manpower and implementation.
So it'll be great to have this in the future. So. Could you wrap this up? I think that
I can wrap it up. So basically, I can summarize that REKS for excited states is a variational approach to describing excited states, which provides accurate description of various phenomena in photochemistry. So that would be probably the shortest wrap up I have ever had. Right, and at this point, I would like to thank for your attention and stop with my presentation.
Okay, thank you very much.
Oh, thank you.
Okay, what a wonderful lecture. Thank you very much. Really energetic, and I think that. He talks about many different things, from the equations and applications and the connections. Maybe it's okay you don't understand at first. Okay, so we will upload this to the web page, the YouTube. Then you can watch later. If you have questions, he is right here. You can give questions. So basically he wants to cover many different things. So I don't think it is easy to understand by first simply listening once his lecture. So, but basically what he has done so far is completely new density functional theory for really strong correlated systems like this. So I think that this is really promising.